Hello my dear students, welcome back to your channel. Hope you all are doing well. Today I am going to start quick revision of chapter 14 of class 11th physics, that is oscillations. In this chapter, different topics to be covered are: first, what do you mean by periodic motion? Then different terms related to this periodic motion. Then this periodic motion is represented by periodic functions. After that, what do you mean by simple harmonic motion and its equations? Then oscillations of a loaded spring and force constant. Then total energy in simple harmonic motion, that is kinetic and potential energy. After that, simple pendulum and its time period. And last topic of this chapter is free, forced and damped oscillations, right? So I will cover each topic one by one. Let us start first with what do you mean by periodic motion, right? Okay, first motion. Motion can be divided into two types. One is periodic motion and another one is aperiodic, or you can say non-periodic motion. Right? Now this periodic motion may be oscillatory or non-oscillatory motion. Oscillatory or non-oscillatory motion. Now this oscillatory motion may be, it can be divided into two types: simple harmonic motion or non-simple harmonic motion. And in this chapter we mainly focus on this topic, that is simple harmonic motion. But before starting this simple harmonic motion, you must know about, because this comes under this heading oscillatory motion, and oscillatory motion comes under periodic motion. So first I will discuss what do you mean by periodic motion, then types of periodic motion, after that types of oscillatory motion. Okay, so let us start. First, what do you mean by this periodic motion? Any motion that repeats itself after regular interval of time, that is called periodic motion. For example, orbital motion of Earth around the Sun, motion of arms of a clock, motion of simple pendulum. These are examples of periodic motion. All these motion repeat itself after a regular interval of time. Here it's shown in the diagram that this stone moves in a circular part and then completes one circle, again moves in a circular part. So this is an example of circular motion. Then these planets revolve around the sun. This is also an example of periodic motion. This bob of a simple pendulum moves to and fro. This is also an periodic motion. All these motion repeat itself after a regular interval of time. Okay, so hope it's clear to all of you what do you mean by periodic motion. Now there is classification of this periodic motion. It may be oscillatory and non-oscillatory motion. Then what do you mean by this oscillatory motion, right? Okay, oscillatory motion means when a body moves back and forth about its mean position. Mean position means equilibrium position. Suppose this is the bob of a simple pendulum and it is at rest at this position. This position is called mean or equilibrium position. Now this bob moves forward, then again come back to its original position, then again moves in backward direction, then again come back to its original position, that is mean position. So this bob moves to and fro, back and forth about its mean position. This type of motion is called oscillatory motion, and this is also periodic motion because it repeats its motion after a regular interval of time. So this oscillatory motion is a periodic motion, but every periodic motion is not oscillatory, right? This point is very important. Every oscillatory motion is periodic, but every periodic motion is not oscillatory. Why? For example, suppose motion of Earth around the sun. Suppose this one is this sun and planet revolves around the sun. So this is an example of periodic motion, but it is not oscillatory motion because this planet or Earth moves in a circular path, not to and fro motion. So it is a periodic motion but not oscillatory. But every oscillatory motion must be periodic. Examples of oscillatory motion are motion of pendulum, motion of mass suspended from a spring, vibration of a strings of a guitar. All these are an example of oscillatory motion. If the body does not move to and fro, then that type of motion is called non-oscillatory motion. After this oscillatory motion may be harmonic or non-harmonic motion. It may be harmonic or it may be non-harmonic motion. So what do we mean by harmonic motion? What do you mean by non-harmonic? I've discussed after periodic function. The periodic motion is represented by this periodic function. Now, what is this periodic function? A function that repeats its values at regular interval of time. For example, trigonometric function, this sine, cosine function, all these functions repeat its value after 2 pi interval. It means this function is periodic function. For example, sine x, and sine x after 2 pi interval, again sine x plus 2 pi becomes sine x. Cos x plus after 2 pi interval again becomes cos x. So these are periodic function, and any function that is not periodic is called aperiodic or non-periodic function. Now next, harmonic function. What do you mean by this harmonic function? A function which can be expressed in terms of single sine or cosine function is called harmonic function. Any periodic function, these harmonic function are periodic function which can be expressed in terms of single sine or cosine function, then that is called harmonic functions, and others are non-harmonic. For example, only sine and cosine means harmonic function, and if it is represented by sin square omega t, 2 sin square omega t, these are non-harmonic function. For example, this is a graph of what? Cos omega t, right? So it starts from this maximum position, after that it repeats the interval after a fixed interval. This is fixed one cycle, and then again repeated the same motion. So this is periodic function. But if you draw a graph like this one, suppose like this one, so it does not repeat its motion after a regular interval of time. So this is not a harmonic. These are non-harmonic function. For if graph is like this one, then this one, then this one, so these are non-harmonic function. Okay. So after this, most important topic of this chapter I'm going to start, that is simple harmonic motion. What do you mean by simple harmonic motion? Okay, a particle is said to execute simple harmonic motion if it moves to and fro about a mean position under the action of a restoring force whose magnitude is proportional to displacement and always act towards mean position. For example, suppose this is the bob of simple pendulum. If you apply some force, it moves forward, then again come back to its original position. Who comes to its original position? There is some restoring force. Under the action of that restoring force, this bob come back to its original position, right now, and this restoring force is directly proportional to the displacement from this mean position, and this restoring force through which the object comes to their mean position is always in a direction opposite to the displacement, right? And this type of motion is called simple harmonic motion. Restoring forces are those forces when a particle displaces from its mean position to extreme position, then a force comes into play which tries to push the object into the mean position or original position, and this restoring force is directly proportional to displacement. If this is the mean position of the object, it moves to, and this is end position, maximum position is extreme position, then when an object moves in this direction, then the restoring force is developed in opposite direction so that it again comes back to its original position. So this restoring force is responsible to move the object come back to its original position, and this restoring force is directly proportional to displacement from the mean position, and you can write this as F equal to minus kx, where k is a spring or force constant. Why this negative sign is there? This negative sign shows that a force, or you can say a restoring force, opposite to displacement. If displacement is in forward direction, then the restoring force acts in backward direction, and this defines simple harmonic motion, right? If this equation is satisfied by any particle, then that type of particle executes simple harmonic motion. It moves under the action of restoring force whose magnitude is proportional to displacement and it always acts towards mean position. So this is about simple harmonic motion. Now equations for simple harmonic motion. How you represent simple harmonic motion mathematically? So you know sine and cosine function is a periodic function, and also single sine cosine function is a harmonic function. So this simple harmonic motion is represented by that simple harmonic function. It means sine and cosine function. So displacement x in simple harmonic motion at any time is represented by x equal to a sine omega t plus phi, or you can say x equal to a cos omega t plus phi. You can use any one, sine omega t plus phi or cos omega t plus phi, but situation is different. When time is measured from mean position, if the body starts from this initial time mean position, then you have to use a sine omega t plus phi. If a body starts from extreme position, when time is measured from extreme position, it means maximum position, then it comes back to its original position, then moves back, then in this way. These are extreme position and these are equilibrium mean position. If a body starts from mean position, then you use this equation. If a body starts from extreme position, then you have to use this cos omega t plus phi, where this a is called amplitude of oscillation, right? This small t is given time. Then this omega is angular frequency and omega t plus phi is called phase. So I will discuss each term in detail one by one. These are the displacement time graph for sine and cosine function. If time starts from this mean position, you have to use this sine omega t plus phi, and this is the graph for sine omega t plus phi. It completes one cycle after time capital T. Half cycle T by 2 and 1 by half is T by 4. This is a graph of a cos omega t plus phi when time is measured from extreme position. It starts from this one and it completes one cycle after a time interval T. So you can use any equation, a sin omega t or cos omega. Answer is same, right? After this, I am going to discuss these different terms: amplitude, angular frequency, phase, initial phase. What is this? Okay. So hope it's clear to all of you, right? Now, some terms related to simple harmonic motion. First one is time period. Time taken by the body to complete one oscillation is called time period and it is denoted by capital T. Suppose the body starts from this position, then it completes one cycle and again return back to original position. So this is time period, capital T, or from here to here again capital T. Okay. Frequency, the number of oscillations completed by the body in 1 second. This is called frequency. Is denoted by nu also, or you can denote it by it f also. And this is given by 1 by time period. Its SI unit is hertz or second. The next one is angular frequency, that is omega. The product of frequency with 2 pi. It means omega equal to 2 pi nu, or you can write 2 pi by t. 1 by t is frequency, so you can write 2 pi nu. Product of frequency with factor this 2 pi, you get angular frequency. Its SI unit is also hertz or second. Now then displacement. A physical quantity which changes uniformly with time in a periodic motion is called displacement. It is denoted by x also or y also in any direction. The body can move. So the quantity which changes uniformly with time, this distance changes with time when you complete one oscillation. So it is called displacement. And what do you mean by amplitude? The maximum displacement in any direction from mean position. This is the maximum displacement at any time. And this one is called amplitude, maximum displacement. Displacement changes with time. When body moves with time, it moves like this one. So its displacement changes with time. But the maximum displacement in both direction, plus A or minus A, this is called amplitude. After that, one more term is there, that is phase, and this is very, very important. What do you mean by this phase? Simple harmonic motion is represented by this x is displacement at any time a cos omega t plus phi. This term cos omega t plus phi is called phase of simple harmonic motion at any time, and it describes the state of motion at any instant. And the quantity this phi is the phase at time t equal to, when at time t equal to 0, this phase phi is called phase constant or initial phase of the simple harmonic motion, and this phase constant is time independent term in the cosine or sine function. This initial phase does not depend on time, it is at time t equal to 0. This is called, that's why it is called phase constant or initial phase. It is independent of time, right? Simple harmonic motion is defined as projection of a uniform circular motion on any diameter of a circle of reference. This point is very, very important. You must remember this point. This simple harmonic motion is projection of a uniform circular motion on any diameter of a circle of reference. Okay, so hope it's clear to all of you. Now, to represent simple harmonic motion, you have to use position, or you can say displacement. When the motion starts from mean position, you have to use xt equal to a sine omega t plus phi, and when the motion starts from extreme position, you have to use xt equal to a cos omega t plus phi. Right? You must remember, you can use any equation. If motion starts from mean position, you have to use a sine omega t plus phi. If the motion starts from extreme position, you have to use a cos omega t plus phi. At equilibrium mean position, x is always 0, and extreme position, x may be plus a or minus a. This a plus a and minus a are amplitude in both directions. So, hope it's clear to all of you. After this, displacement, velocity in simple harmonic motion. How you find velocity in simple harmonic motion? I am going to find in both cases. When the motion starts from mean position, you have to use this equation, xt equal to a sine omega t, and velocity is what? Differentiation of this displacement, dx by dt. So when you differentiate this one, sine omega t, you get omega cos omega t, and this, you can write this cos omega t in terms of sine omega t is under root 1 minus sine square omega t minus plus phi, and this a sine omega t is what? X by, this sine omega t is x by a, right now. So in place of this sine square omega t, you have to write x square by a square. So velocity becomes a omega under root 1 minus x square by a square. At mean position, what is the value of x? X is 0. So at mean position, velocity is maximum, a omega. At extreme position, x may be plus a or minus a, and that position, if x is plus a or minus a, this velocity is 0, since the particle is at rest at that position. In the same way, when the motion starts from extreme position, you have to use this equation, a cos omega t plus phi. You can use any equation. Answer is same. If you differentiate this one also, in this case, you get velocity minus a omega under root 1 minus x square by a square. Again, at mean position, it means x is 0, velocity is maximum, and at extreme position, when at x equal to plus minus a, velocity is 0, since the particle is at rest. So hope it's clear to all of you which equation you have to use. If the motion starts from mean position, you use sine omega t plus phi. If the motion starts from extreme position, you have to use cos omega t plus phi. Any equation you can use, answer is same. So this is about velocity in simple harmonic motion. After that, acceleration is simple harmonic motion. When you differentiate the velocity, you get acceleration. So here also you can use any equation. Displacement, here I am using, when the motion starts from mean position, x equal to a sine omega t plus phi. When you differentiate this one, you get a omega cos omega t plus phi. And again, to find acceleration, you have to differentiate this velocity. And again, this a cos omega t plus phi means this one. Differentiation of this, sorry, here is not written, minus differentiation of this cos omega t plus phi is minus omega sine omega t plus phi. So this sine omega t plus phi is nothing but x, so you can write minus omega square is x. This is the formula for acceleration. At mean position, again x is 0, so at mean position acceleration is 0, and at extreme position x may be plus a or minus a, so omega is maximum at extreme position, omega square a. At plus a, acceleration is minus omega square a, and at minus a, acceleration is plus omega square a. Negative sign indicates that direction of acceleration is opposite to the direction in which displacement increases. It means it is always towards mean position. If suppose this is the mean position and body is moving in this direction, so acceleration is acting in opposite direction. If a body is moving in this direction, so acceleration is acting in this direction. It is always acting towards the mean position, opposite to the direction in which the displacement increases. And when the motion starts from extreme position, you have to use same equation. Only in place of sine omega t, you have to use cos omega t plus phi. Answer is same. In that case, acceleration is omega square x. So at mean position again, acceleration is 0, and extreme position, acceleration is omega square a. So hope it's clear to all of you about velocity, acceleration, displacement in simple harmonic motion. Now these are graph for displacement, velocity and acceleration. When the motion starts from mean position, then in that case you have to use a sine omega t plus phi. Right now, use this equation xt equal to a sine omega t. It means the motion starts from mean position. So at mean position, time is 0 and x is also 0, right? So body starts from this mean position. At that time x is 0, and then it completes one rotation like this one in time period capital T. Okay, and what is the formula for this velocity? Velocity, when you use this equation, velocity is maximum at mean position. So at mean position at time t equal to 0, velocity is maximum at mean position. Then again it completes one cycle and again it returns back to its original position. And then acceleration is what? Acceleration is minimum at mean position right now. So acceleration is 0 at mean position. Then again it completes one oscillation. So this one is displacement time graph, velocity time graph, acceleration time. In this one, velocity is maximum at mean position. Suppose this is the bob of the pendulum. This one is mean position. So here velocity is maximum and acceleration is 0, and this is the extreme position. Here velocity is 0. When the motion starts from extreme position, it means from here. At extreme position, velocity is 0 and acceleration is maximum. In this case also, this extreme position, velocity is 0 and acceleration is maximum. So when the motion starts from extreme position, in that case displacement is also maximum, displacement time graph. Velocity is 0 at the extreme position right now. So V is 0 at the extreme position and acceleration is maximum at the mean position. Why negative side? When the body moves in this direction, acceleration is in opposite direction, minus a omega square, right? So these are displacement time graph when the motion starts from extreme position, and this one is from motion starts from mean position. Hope it's clear to all of you. After this, I'm going to discuss force law in simple harmonic motion, then energy in simple harmonic motion. You know, acceleration of body in simple harmonic motion is what? A equal to minus omega square x. We already derived this one, right? Now from Newton's second law, what is force? Force is equal to ma. So when you put this value of a in this equation, F becomes minus m omega square x, and this m is mass of the body, omega is angular frequency. These two are constants, so you can replace this by k, and you can write F equal to minus kx, where this k is what? K is omega m omega square. From here you get omega equal to root over k by m. This is called angular frequency, and k by m omega square is a constant, sometimes called elastic or spring constant in simple harmonic motion. So you can say that in simple harmonic motion, F equal to minus kx means F is directly proportional to an opposite direction of displacement. This force is proportional and opposite to the displacement. If this satisfies, you can say that the body executes simple harmonic motion, F equal to minus kx. And how you derive this one? Using acceleration and Newton's second law of motion, you derive F equal to minus kx, where k is m omega square and omega becomes under root k by m. You remember this formula, omega equal to under root k by m. K is a spring of force constant, m is mass of the particle. Now next one is energy in simple harmonic motion. When a body executes simple harmonic motion, it may have both type of energy, kinetic energy as well as potential energy, right? So at which position kinetic energy is maximum, potential energy is maximum, what is the value of total energy at any time? I'm going to derive that one. First one is kinetic energy. Kinetic energy is what? Half mv square, and v already we derived now in the previous slide. V is what? A omega under root 1 minus x square by a square. You put this value here in place of this v square, you get half m omega square a square minus x square. This is the equation of kinetic energy. And at mean position, this x is what? X is 0 at mean position. So at mean position, energy is maximum. How much? Half m omega square a square. And at extreme position, x is a. So this a square minus a square is 0. So at extreme position, energy is 0. So suppose this is the bob of the pendulum and this is the mean position, and this one is extreme position and this one is again extreme position. At this position, at x equal to 0, energy is maximum because the V is maximum now. So kinetic energy is maximum at mean position and kinetic energy is 0 at this extreme position. Okay. Now next, potential energy. Potential energy is what? Half kx square, and k you get how much? You've got the value of k. K is m omega square. So potential energy becomes half m omega square x square. Again at mean position x is 0. So potential energy is 0 at mean position. It means at mean position potential energy is 0 and at extreme position x is a. So at extreme position potential energy is maximum at extreme position. Here V is 0.
Here's what I found online.
So these are about its kinetic energy and potential energy. Kinetic energy is half m omega square a square minus x square, and potential energy is half m omega square x square. Now at some place potential energy is maximum, at some place kinetic energy is maximum, but total energy always remains constant. So what is the value of this total energy? Next slide is there. The total energy is given by sum of kinetic energy plus potential energy. Kinetic energy is half m omega square a square minus x square plus potential energy is half m omega square x square. So here this term and this term cancel, only left with half m omega square a square, and this is the expression for total energy in simple harmonic motion. This mass of the particle is constant. Executing simple harmonic motion, omega angular frequency is constant, amplitude is also constant. So all these terms are constant. So total energy is always constant in case of simple harmonic motion. So you can write in this way one line: when a body executes simple harmonic motion, its energy changes between kinetic and potential, but the total energy is always constant at any displacement from the equilibrium position. This is the potential energy graph with displacement. You know, at this is in mean position x equal to 0, and this one is extreme position x equal to plus a, and this one is left extreme position x equal to minus a. You know, at the mean position kinetic energy is maximum and at extreme position kinetic energy is minimum. So this is the graph for kinetic energy, right? K. And at mean position potential energy is minimum, at extreme position potential energy is maximum. So this green one is graph for potential energy, but this straight line represents total energy and it is always constant, half m omega square a square. Only kinetic energy is converted into potential energy at some point. At some point potential energy is converted into kinetic, but total energy always remains constant. So total energy of a particle executing simple harmonic motion is directly proportional to mass of the particle, directly proportional to a square of its frequency, and directly proportional to a square of its amplitude. And this is the graph for total kinetic energy and potential energy with displacement, and this one is graph for energy with time. This green one is potential energy with time and this red one is kinetic energy with time, and graph is like this one. Okay, so hope it's clear to all of you, and this graph is also very important: energy with time and energy with displacement. Okay, after this one table is there. If displacement, then expression of equation, you can write displacement x equal to a cos omega t, and x varies between plus a and minus a. Velocity time graph, velocity becomes this one, acceleration becomes this one. So you must remember this table, take a screenshot of this one right now. After this only one or two topic is left. Next one is body executing simple harmonic motion, and best example is oscillation due to a spring. Now suppose consider a spring, this one, and a block of some mass is attached to this spring. Okay, so consider a block and it is pulled one side and then it is released. Then it executes to and fro motion about a mean position. In this diagram, this is the equilibrium position of the block. This one is x equal to 0, equilibrium position or mean position. Now if this block is pulled or pushed and then released, suppose it pushed or pulled in this direction, then released, then again pulled in this direction, then it is released, then it executes simple harmonic motion, right? So you can write like simple harmonic motion f equal to minus kx. If you pull this block in this direction, x is positive, then here restoring force is acting in negative opposite direction. This is the stressed position. When this this bob is compressed in this position, displacement, and then restoring force is acting in this direction, opposite direction. This is the compressed position, and this one is equilibrium position at x equal to 0. This one is stressed position, this one is compressed position. In both cases, restoring force acts on the body, which is opposite to the displacement. If here x is positive, restoring force is acting in negative direction. Here displacement is in negative direction, restoring force is acting in this positive direction. So this executes to and fro motion. So it is an example of simple harmonic motion. So you can use fx equal to minus kx, where k is a spring constant. This is same as the force law for simple harmonic motion, and therefore you can use, like in simple harmonic motion, omega is equal to root over k by a, and time period of this spring is 2 pi under root m by k. This is the expression for time period in case of this one. Okay, so hope it's clear to all of you. After this, next is different connections of springs. When the spring is connected in series and when the spring is connected in parallel, and what happens to the spring constant. Suppose there are two springs having these two are connected in series. One having a spring constant K1 and another having a spring constant K2. So when you connect the two springs in series combination, then the spring constant of the combination is given by 1 by k equal to 1 by k1 plus 1 by k2. You must remember this formula. When the springs are connected in parallel, like this one is first spring having a spring constant k1, second spring having a spring constant k2, and these two are connected in parallel combination. In that case, total spring constant of the combination is given by k equal to k1 plus k2. So you must remember these two formula. These are useful when you solve the numericals. When one spring is attached to two masses m1 and m2, then in that case total mass is given by m1 m2 by m1 plus m2, and time period is given by 2 pi under root m by k. You must remember this formula also. After this, one last body which exercits simple harmonic motion is simple pendulum. You know what do you mean by simple pendulum? A simple pendulum consists of a heavy point mass body suspended by a weightless, inextensible and perfectly flexible strings from a rigid support. This one, heavy point mass suspended by this weightless and flexible string having length L from this rigid support. This is point of suspension. Suppose let T be the time period to complete one oscillation. If you apply some force, this bob moves in this direction, and suppose tension is acting in this direction, T dash. Okay, T dash is the tension. At equilibrium position, tension is balanced by this weight of the body, mg. T dash is balanced by mg. But when this body moves for a small displacement theta, it moves with some angular displacement theta, it comes to this position, right? And at this position, different forces acting on the body. Here, this is the mass of the bob mg. It is divided into two components, mg cos theta and mg sin theta. This mg cos theta is balanced by this tension in the spring, but this mg sin theta is acting in this direction, and this acts as a restoring force. It is responsible for keeping the body to its original position. So this mg sin theta acts as a restoring force in this case. So restoring force, you can write is that body moves in this direction, so it is acting in this opposite direction, minus mg sine theta. For a small displacement, sine theta can be written as theta, and this theta is equal to x by L. This x is displacement, right? L is length of the string and theta is angular displacement. So you can write theta is equal to x by L. So restoring force becomes minus mg theta. In place of theta, you can write L into x. Now acceleration, you know, force per unit mass. So you get acceleration minus glx. Also, you know, for simple harmonic motion, acceleration is given by minus omega square x. So when you compare these two equations, you get omega square equal to g by L, and time period of oscillation is t equal to 2 pi omega. You put the value of omega here. Omega is under root what? Omega is under root g by L. So when you divide it by this omega, it becomes time period equal to 2 pi root over L by g. Hope it's clear to all of you how you find the time period of a simple pendulum. Simply you find the restoring force minus mg sine theta. For a small angular displacement, sine theta becomes theta and theta is x by L. You get restoring force as this one. Now you get acceleration is force per unit mass, and in case of simple harmonic motion, acceleration is minus omega square x. When you compare these two, you get time period as 2 pi under root L by g. So this is the case of simple pendulum. Now after this, there are one or two definitions are there. First one is different types of oscillation. First one is free or undamped oscillation. What is this free or undamped oscillation? In this type of oscillations, the amplitude and time period remains constant. It does not change with time. The amplitude always remains constant. It does not changes with time. This type of oscillations are called free or undamped oscillations. There is no damping in this case. No frictional force exists in this case. What do you mean by damped oscillation? Type of oscillation in which amplitude of the oscillating body decreases with time. Suppose the body starts its motion from this position and its amplitude decreases with time, and at last it becomes 0. Why the amplitude decreases with time? Due to some friction, like damping forces like frictional force, viscous force, all these forces acts on the body and its amplitude decreases exponentially because of this damping force. This is called damped oscillation, but in this case free oscillation, amplitude remains constant with time. Now one more type of oscillation, that is forced oscillation. What is this? When the damping force acts on the body, its amplitude starts decreasing with time, right now. So to maintain its amplitude, we have to apply some external force. So the forced oscillation refers to type of oscillation or vibration in a body which vibrates under the influence of an external periodic force. This type of oscillation is called forced oscillation. It means when a body oscillates with the help of some external force with a frequency different from the natural frequency of the body, then the oscillations are called forced oscillation. Then what is this resonance condition? When you apply some external force, the body vibrates with a frequency different from the natural frequency of the body. But there is one condition: when the frequency of this external force is same as the natural frequency of the oscillator, then this state is called state of resonance. And in this case, frequency of external force is equal to natural frequency of the body, and that case frequency is called resonant frequency. So this is the condition of resonance, when natural frequency of the body is equal to frequency of the external force, right? So hope it's clear to all of you. With this, I am going to end my class. Hope you like this one short series. If you liked it, then don't forget to subscribe my channel. Okay students, so keep revising and stay tuned with this channel. Thank you.